So let's move along to Script2C in Math156. This rather short script covers moments, skewness, and kurtosis, and we've moved from the very data-oriented in Script A to the very mathematical in Script C. This topic, for some reason, has fascinated students in previous offerings of the course. You might want to pause the video and read section 8.7, that's an appendix, and 2.7 of the textbook, both of which introduce these ideas. The authors calculate some of these quantities by evaluating integrals. Since this is an R script, I'm going to have R evaluate the same integrals numerically. Let's start with moments of a distribution. This is a probability concept. For any probability distribution, you can calculate the moments, which are the expectations of the various powers of the random variable. The nth moment is the expectation of x to the n. If you subtract off the expectation before raising to the nth power, you get the nth central moment, which is what's usually of more interest. So let's try with a finite population. We'll go back to our standard dice example and read in a data frame for the roll of 3 dice, and then save a new vector, which is the sum of the rolls on the 3 dice. We'll call that x. That's a perfectly good random variable. We can plot a table of it, and you can see the vertical bars give the probabilities of all the rolls up through from 3 up through 18. If I had a little more real estate to spare, 10, 12, and so on would show in the labels, but I want to reserve the space for my script. To get the first moment, I ask for the mean of x. To get the second moment, I ask for the mean of x squared. That turns out to be 119. If I ask for the second central moment, I ask for the mean of x minus mu quantity squared. That's the variance, 8.75. I think you've seen that number before. The mean of x cubed is the third moment. The mean of x minus the expectation cubed is the third central moment. That's equal to 0 for the simple reason that this is a symmetrical distribution. I can calculate the fourth moment, and I can calculate the fourth central moment. Neither of these has a numerical value that makes any particular sense to me. And in fact, what's conventional to do is to make these third and fourth moments invariant to scale change, so that if I did the same thing for twice the die roll, I'd come up with the same numbers. Here's how this is done. This is discussed in the math notes. First, you take the square root of the variance to get the population standard deviation, conventionally denoted by sigma. And for skewness, which is based on the third central moment, you divide by sigma cubed. If you double everything, you will multiply the third central moment by 8. You'll multiply sigma by 2, and the result in the skewness will be not to change it at all. And sure enough, the skewness comes out 0. For the kurtosis, what's done is really quite strange. Dividing by sigma to the fourth seems obvious. Why subtract 3? Well, if you've already looked at the math notes, you'll know that this is because a normal distribution has a kurtosis of 3, and therefore positive kurtosis means fatter tails than a normal distribution. Negative kurtosis means skinnier tails. Now, in this particular case, the possible values cut off at 3 on the low end and 18 on the upper end, so you can argue there are no tails at all, and that's why the kurtosis is negative, like my Manx cat. Let's look at an example where the skewness is not 0 because the distribution's not symmetrical. We'll spend a lot of time on Poisson distributions, but for tonight I'll just give you an example of one. Here I have plotted the Poisson distribution with a parameter lambda equals 5. That means the expectation is going to equal 5. And I've plotted this from 0 to 15. Beyond 15, the values are so small as not to be worth plotting. This will turn out to be the limit of a binomial distribution when you have lots and lots of trials, each with a very small probability of success. Now I want to calculate the expectation, mu, the first moment. So I sum from 0 to 30 the value that I get, that's the number 0 through 30, multiplied by the density function for the Poisson distribution with parameter 5 evaluated at 0.30, and I get precisely 5. If I were writing this mathematically, I'd do the sum from 0 to infinity, but R seems to choke if I ask it to do infinite sums. If I want to get the variance, I say what I need to do is take the vector of values 0 through 30, subtract the expectation mu from all of them, square that value, and then multiply by the probability of getting that value given by the Poisson function. That's the second central moment. I got 5 again. Did R make a mistake? No, that is in fact correct. The Poisson distribution has the same values for the expectation and the variance, and in a week or so you'll be able to prove that yourself. Sigma is the standard deviation, the square root of the variance, and I'm going to need that as soon as I compute the third central moment, because the skewness is the third central moment divided by sigma cubed. This comes out to 0.44, and if you've looked at the Math Notes video, you'll know that positive skewness means a long tail to the right, negative skewness means a long tail to the left, so that's reasonable. Finally, I compute the fourth central moment, which comes out to precisely 80. It's interesting that it's an integer. And to compute the kurtosis, I divide that by the fourth power of the standard deviation and subtract 3. I get 0.2. That means this has just slightly fatter tails than a normal distribution. We can do the same thing for continuous distributions, but now we need integrals instead of sums. So let's start with the normal distribution, expectation of 3, and variance of 4. Notice I use dnorm x, 3, 2 because the last argument for dnorm is the standard deviation, not the variance. I need the square root of 4. The function curve will plot this. I needed to experiment a little bit to get appropriate values of from and to for a nice looking plot. And to compute the expectation, what I have to do is to define a function equal to x times the density function and then integrate it. For some reason, R is perfectly happy with infinite limits of integration. Now the syntax of this is a little bit tricky. I'm calling the R function integrate. Integrate wants a function, and specifically it wants a function of x. So I say function of x defined by the formula x times the normal distribution density function for mean 3 and standard deviation 2, and please integrate that from minus infinity to infinity and show me the result. And it says the result is 3 with absolute error equal to 10 to the minus 6. I don't care about the absolute error. Of course it's small. I can get just the value I want by taking the result of this and saying $ value. Then I get just the number 3. Let's do the same thing to get the second central moment. Now in defining my function, I use not x, but the quantity x minus mu squared. And in that case, I got 4, which is what I expected for the variance. When I take the square root of the value part of that, I get 2. The skewness is clearly 0 because of symmetry. The kurtosis, however, is something that's of interest to us. Now, I actually, in the math notes, did this calculation of kurtosis analytically. Here I'm doing it numerically by defining the function x minus mu to the fourth times the normal distribution density function to get the fourth central moment, and then dividing that by the fourth power of sigma and subtracting 3, and I get a value. I was supposed to get 0. I get minus 1 times 10 to the minus 12. That's close enough to 0 for my taste. Another example that's done in the textbook is the exponential distribution with lambda equals 1. This is done in the textbook by antiderivatives, which were in turn evaluated by integrating by parts an unpleasant number of times, but we can do them numerically. Let's plot this density function from 0 to 6. Let's define a function which is x times this density function, integrate it from 0 to infinity. We get 1. That's what's to be expected. And then let's take x minus mu squared times this density function and integrate it. The value is 1 again. Sigma is 1. And that confirms the result shown in the textbook that for this distribution, both mu and sigma are equal to 1. But the skewness is not going to be 0 in this case. You can tell that by looking at the long tail to the right. So I compute the third central moment in the same way, divide its value by sigma cubed, and I get a skewness of 2. That's exactly what I computed in the math notes, and that's exactly the result that the textbook got. Finally, I can compute the kurtosis, and in this case, the kurtosis is 6. You can confirm this yourself by calculus. So far, we've worked with probability distributions, but in the real world, you work with samples, and you can compute higher moments of samples. Let's do this by generating our samples randomly. Let me correct this typo so it doesn't show up next time someone looks at this. Not smapples, samples. Okay, so let's draw random samples from this exponential distribution with lambda equal to 1. 10,000 samples is perfectly reasonable for my computer. And if I call for the head of this vector, you see I get a bunch of numbers. They're all positive, and the large ones look a bit on the unlikely side. To look at more data, I plot a histogram, and that lines up fairly well with my probability density function. If I take the mean of this vector, I get the so-called sample mean. I'll give this the conventional name x dot bar. X dot bar is not precisely equal to 1, but it's mighty close. If I take the mean of x minus the sample mean squared, that's not precisely the variance. It's the sample variance, and it is fairly close to the value sigma, which is equal to 1. It's a little bit low. You might have said, oh, you made a mistake. You should have divided by n minus 1. But with 10,000 samples, dividing by 10,000 or 9999 doesn't make much difference. I can go after the third central moment and compute the sample skewness. Here the theoretical value is 2. Wow, usually I get something that's way off, but this time I lucked out and got 1.993. And if I finally go after the fourth central moment and calculate the kurtosis, I get 5.63. The correct value, or the theoretical value, is 6. If you want to get values that are closer to the theoretical value and you've got a fast computer, repeat this with 100,000 samples, and the sample moments will agree more closely with the theoretical moments. Now, the problem was with the long tails here. I can eliminate long tails by using the uniform density function. Here's a plot of d-unif. It's 1 from 0 to 1, 0 to everywhere else. This has shorter tails than my Manx cat. Let's generate 10,000 samples from this by using the r-unif function. You can see I'm getting a bunch of numbers all between 0 and 1. And if I plot a histogram, it's consistent with being uniform. It's always a surprise to novices to see how great a discrepancy there is, even if you take as many as 10,000 samples, which is a realistic thing to do only with a good computer. So I'll calculate the sample mean, x dot bar, should be close to 0.5, and it is mighty close. Let's compute the second sample moment and take its square root. And then, since the sample variance is supposed to be 1/12, I'll square this and multiply by 12. I should get a number that's close to 1, and indeed I do. Theory's working fairly well. The third central moment, of course, is very close to 0 because this distribution is symmetric. What's interesting is the kurtosis. So I take x minus x bar, raise it to the 4th power. That gives me the 4th sample moment. Divide by s to the 4th, subtract 3 to get the kurtosis. And what do you know? That's about as large a negative kurtosis as you're ever likely to encounter. It's minus 1.19. And with that, I conclude my discussion of moments.